This is the second lecture for Chapter 11 on intermolecular forces in liquids. So, starting off the first slide here, we look at is some of the differences between dipole moment and dispersion. And typically, we like to say that dispersion is the weakest of the values. And I guess if all things are equal, yeah, I guess it is weaker. But it really has some things that we have to take a look at and see what it compares. So listed here is saying, well, everything's kind of the same. Well, if they're the same, then dipole-dipole interactions are probably going to be more dominant. But if we have a comparison where one molecule is a lot larger than the other, then the dispersion force is probably going to be what's going to influence the physical characteristics, boiling points, melting points. So something we look at here, and this is going to bridge into our next topic, is we see this trend which is pretty consistent. Well, I got the wrong thing pointed up here. Let me switch this over to my marker. And we see a nice easy comparison. We'll focus on the red one here and say, okay, I can see what a trend is here, but except for this high point. And these are all based on families. The only thing we're switching out here is the oxygen for a sulfur for a selenium on down the line. And we can do the same thing for this halogen group. We go from fluorine to chlorine and then down the line, and so on. So what we see are these guys here are kind of screwing up my pattern. And what we notice is those happen to be my nitrogen, oxygen, fluorine atoms, which are quite electronegative. They're also quite small. So what we're noticing is those are kind of standing out a little bit within the group. We notice that the boiling points over here on the y-axis are going up as they're moving along with the molecular weight, which is the whole London dispersion. But those three atoms are a little bit different. So we'll mention those with hydrogen bonding. So if you have those three atoms in the mix, nitrogen, hydrogen, or fluorine, and there's a hydrogen attached to it, you'll notice that you're going to have this hydrogen, which has its electrons pulled away from it by this electronegative atom. It's kind of exposed. It's just pretty much just a positive proton hanging out there, and it is going to be attracted to the electron pair from another nitrogen, oxygen, fluorine, because again, it's electronegative. So you're going to have this attraction towards that, and that's called hydrogen bonding. It's a very strong dipole-dipole interaction, and it gets that special name. Okay, that's not going anywhere additionally, so we'll just leave that. Another one, so we're kind of moving outside of those other three van der Waals forces. This is an ion dipole, and we're familiar with this maybe with hydration. So for example, you have water molecules, these red-ish looking particles, hydrating a particle. So this is just a salt water solution. You have the positive hydrogens being attracted to the negative chlorine, and then you have the positive sodium being attracted to the negative oxygen in water. So this is called an ion dipole interaction, the ion being the sodium and chloride, and the dipole just being water. So a way of characterizing this, I won't spend any time on this, but you can take a look as far as going through a flow chart, noticing that we have 5 different types here. The van der Waals typically are classified as far as dispersion and dipole. Hydrogen bonding, depending upon what category you're looking at, may include that in the van der Waals, but sometimes it's left kind of on its own. So it's one of those intermolecular forces that's kind of somewhere close to the van der Waals. Okay. Looking at some other properties within there. So we've looked at as far as what's affecting the boiling points and the melting points of these. There's some other ones that we'll look at here as well. So this one here being viscosity, which is just a definition, and it just pretty much means resistance to flow. Viscosity, resistance to flow. And we notice that these particles all kind of look the same, hexane, heptane, octane down the line, but we notice that the viscosity values listed over here go up as they're moving along. And the only differences that they have is the carbon chain is increasing. So again, This is the stickiness or the attraction for these particles for each other. So as the carbon chain increases, there's more attraction for each other and they have more resistance to flow. Surface tension is a similar idea, that the particles have attraction to each other. So in this case we look at surface tension with water. The water particles, because they're positive and negative, they have different sides, this very strong dipole interaction or hydrogen bonding, and they're kind of attracted to each other. So at the surface you have this location where you have this non-attraction to the outside or the air or the surface, whatever you want to have it. So it kind of pulls in and almost creates like a film. So that's where you have this surface tension. You can kind of get that bubble where you have a drop of water sitting on a table. It almost creates like a bubble because it's more attracted to itself than anything on the exterior. We won't spend any time here. This is just some of those phase change names that you're quite familiar with. If you're not, here you go. Spend some time looking at it. And this is just looking again some more definitions as far as what are the heats of fusion, vaporation, and sublimation. We rarely ever will talk about the heat of sublimation. It's pretty much always the other two because we're talking about some particular pressure that we're working with and it just doesn't come into play. And apparently I have this slide on here a few times. Alright. A heating diagram. You're familiar with this from last year. You guys, I'm sure, did this in chemistry class. Looking at as you add energy to a substance, and we say we heat that substance, the temperature may or may not go up depending upon what's happening to the substance. So, for example, I start with a solid. It's really, really, really cold. So as I heat the substance, the temperature goes up. But then you hit this plateau in which that solid is turning into a liquid. And then the temperature doesn't go up at all. Think of my ice melting. The temperature doesn't go up until the last bit of ice has melted. And then once you hit the liquid state, bam, whoops, come on. The temperature starts to go back up until you hit another plateau, which is in which the liquid is turning into a gas. And then that process goes on until all the liquid boils away. The temperature doesn't go up. So something interesting, if you're making food on the stove and the water is boiling like crazy, the temperature isn't any different as if you had a very mild boil, if that makes sense. So until all of that liquid is gone and turns into a gas, the temperature doesn't go up. And then once again, it goes up once you have just steam or the gaseous phase. Alright, vapor pressure is getting close to the last lecture we have here. So actually I'm going to go ahead and stop and we'll finish the lecture up after this one.